Load the image off of Canvas, okay, this one. If you click this one, you'll get basically the starter image from Raspberry Pi. So that's what I started with, and then I updated stuff and installed a few things and did some configuration so that you guys wouldn't have to do it. So I'd go ahead and just download my image unless you like really are a Linux pro. Which does anybody have any experience with Linux before this class? Okay, that's what I thought. Um, so you'll you'll choose, you'll click this, and then you'll scroll down to the bottom and you'll say use custom image, and then it'll open up a file browser and you'll select that file that you downloaded. Choose storage. You'll click this, and when you have a micro SD card, it will appear there. So you'll select that, and then you'll hit write, which is obviously grayed out right now. It'll take a while to write it to the SD card and then verify that it wrote everything correctly. And then you're good. You can pop it in your Pi and it's ready to go. Okay. Okay. So does that make sense? That part's pretty easy. Okay. So let's go over to the Pi now, because there's a second step that you'll have to do after you put the image onto the SD card, you put it into your Pi, you power on your Pi. Okay, so that part. Okay, so when you when you power up the Pi, it may take a minute to boot up. Okay, but it will. Did I hit shutdown or log out? It'll look like this. Okay, there are two users installed. There's mine and a generic one that I just called CSC student. Okay, the password for it I'll write down on Canvas. Okay, I'm not going to live stream that because that would be silly. Okay, um, and you can change them if you want the password. You don't have to, but in particular, the default password. This is also the same image as what's on the 4 Pis upstairs in the computer lab. So when I was making this image, I was making it both for you guys, for your individual Pis, but also the ones for upstairs in the lab. Okay, so yeah, good. Okay, so I'll go ahead and log in as me. Okay, so once you log in, you'll see it looks like this. Okay, and I've taken the liberty of installing a few pieces of software for you guys. In particularly, I installed VS Code, which I think is a IDE that a lot of you guys are already familiar with and like. So I'll pretty much use that. It'll tell you if there's updates. I put in widgets for CPU activity and temperature and time, and I'm pretty sure I put it in 24-hour time. You're welcome. Um, yeah, then you can install more software. So if you go to preferences, you can do add and remove software. So for example, you can put Open Office on here and have Word and spreadsheets and all of those kinds of things that you might like for other reasons. But all the stuff that we need is basically just the IDE, a web browser, and a file browser. Okay, so when you after you first power on the Pi, after you've used my image, okay, you need to do this command: sudo res pi -config. Okay, and it's going to pop up with this thing. Okay, and then there's advanced options. You want to hit expand file system. You'll run that. It may take a minute, and then it will say blah, blah, blah. And then you'll need to reboot the thing, and it'll be good. Okay, because essentially what's going to happen is the image that I made is only 9 gigabytes. It's going to write that to the first 9 gigabytes of your SD card. All your SD cards are bigger than that. So when you first power it up, you're only going to see 9 gigabytes worth of space available with almost no free space, because I trimmed off all the free space so that that image would not be gigantic. When you expand it, it's going to say, oh, the SD card, this partition, I can make this much bigger to fill out the rest of the SD card, and then you'll have a crap ton of free space. Okay, so that's the purpose of that. Okay, so does that make sense? So do that first. Don't install any updates. Don't do anything. Do it, reboot it, and then you'll have the full SD card worth of space. The SD cards you guys have, 32 gigs. I mean, that's way more than you'll ever need. So, yeah. Okay, and then finish and reboot. I'll hit no for now, just to save time. But that's it. Okay. And then the other thing that you may need to do, okay, is if you are using this in your room or whatever, and there's not a wired Ethernet connection, if you've got a wired Ethernet connection, use it. Just always. Wired is always better than wireless. Okay, if you don't, it's kind of the same process you have to go to get your Xboxes and stuff onto the network, right? You have to connect to the Wabash IoT network. Yeah, you guys know that, and you have to register your device every year by putting in the hardware address. How do you get the hardware address off of this? Well, the Xbox, it just pops up in the menu and it's pretty easy. It tells you. Here you have to do ifconfig, oops, WLAN 0, and it will tell you this thing right there is the stuff that you have to put into the website, the ether address, okay? You only have to do that for the wireless, not the wired, okay? Yeah. Yeah, you connect it to the Wabash IoT, but you have to pre-register the device on the IT website, right? So it'll have you log in, it'll have you put in that code, and then it'll you can give a description like Artie's Raspberry or whatever, and then submit it, then connect the machine to Wabash IoT. Okay, so this is how we keep like townie scrubs from getting on our network. Okay, um, okay, makes sense. That's not that hard. Okay, so uh, because this is y'all's first, probably any of y'all's first experience with Linux. Okay, so what is Linux anyway? Well, what is Windows? Okay, so what is an operating system? Yeah, Windows is an operating system. Mac OS is an operating system. Linux is an operating system. What's an operating system? Yeah, an operating system is a gigantic program, okay, that allows you to run other programs, and it manages what's running and what's not running and file systems and all of those sorts of things, okay? Um, and prevents you from doing things that would be bad to the computer. It, if you're running like 6 programs at once, it keeps track of who's active at any moment. It allocates resources to all of those different programs so that you can use your computer and enjoy yourself. Okay. These didn't used to exist. Okay. So um, the computers in the say 80s had very, very, very bare bones operating systems. So how many of you guys ever booted up a computer when you were a kid and it was basically just a black screen that looked kind of like that, right? Your old DOS things, and then maybe you typed in Win to get into Windows to play solitaire or whatever. Yeah. Okay. Um, so you were running DOS, okay, or Microsoft's version of DOS, MS DOS. That was an operating system, but it was basically a text only one. It wasn't until the 80s that they released Windows, which was an add-on that sat on top of DOS that gave you this graphical environment where you could resize Windows and it looked kind of like a virtual desktop. In fact, back in the day, they really leaned heavy on that imagery, and it looked like you were looking at somebody's desk from the top down, like a literal physical desk. Okay. But then you had a mouse and you could play games and you could do all of these things. But DOS, one of the early operating systems, when you first booted it, you were in this a command prompt, a terminal. That's it. So flash back to the 70s. Okay. What did a computer look like in, say, the 1960s or 70s? Yeah, it was a giant, like it filled a room. Okay. And then they shrunk a little bit, and most of it or might be the size of a refrigerator. Okay, and you might have multiple modules of it sort of next to each other, so it took up part of a room. Okay, but there were things that could fit in a decent sized space. How did the user interface with that machine? Yeah, through usually a dumb terminal. Okay. So you would sit down at a station that would have a display and a keyboard and basically very, very simple electronics in it that would display stuff and you could type stuff, but it was wired to that big machine. And so you could have one computer over there in the corner and then 30 terminals scattered across campus that are all wired to it, and different users could get on and use the computer um, at all at the same time, all at different times, and the big computer would manage. Okay, you've got this much space. You submit this job, and it would manage all of that. Okay, so one of the early multi-user operating systems that ran on these big computers to do all of this was called Unix. Okay, it was developed at Bell Labs, and uh, Linux is a derivative of it in some sense. Okay, the Mac OS is also a derivative of it in some ways. Now, that said, doesn't my Raspberry Pi look very different from the way a Mac operating system looks? Okay, the graphical interface is very different, but not all, but a lot of the underlying stuff that's sort of under the hood that you don't really see is actually they're cousins of each other. Okay, Windows is a completely different family line from those. Okay, so Linux uh, is a Unix derivative, if you will, that was designed for microcomputers. Okay, so what is the difference between a microcomputer, a mini computer, and just a computer? Well, the computer took up the whole room. A mini computer was the refrigerator size, and a microcomputer is a thing that sits on your desk. These started to become commercially available in the late 1970s and really hit their heyday in the early 1980s. Okay, of when that revolution happened. Okay, um, so Linus Torvalds in the very early 1990s, like 1991, decided to start writing his own little Unix variants, basically as a student project. He was a computer science major at, I think, the University of Helsinki in Finland, in Scandinavia. I'm pretty sure it was Finland. Um, and he's like, yeah, I'll try this out and see what I can do. And one thing leads to another, and now it's a major thing that like companies use, right? So lots of servers are running some flavor of Linux. The Raspberry Pi is using a customized version of Linux. Um, so think of like Linux and Unix as being like second cousins twice removed, or whatever the heck all those terms mean, right? They're kin, but they're kind of far apart in the family tree. And in Arkansas, it would be legal for them to get married, uh, which is kind of scary. But um, oh, come on, I don't get more laughs out of that one. Okay. Um, Linux distributions are more like brothers and sisters or maybe first cousins. Okay, so there are lots of different flavors of Linux. There's Ubuntu, there's Debian, there's Red Hat, there's Mint, there's lots of these different things. Okay, those are more like brothers and sisters. They're much closer to each other and a lot of the underlying stuff under the hood is the same, but the way it's configured and possibly the way it looks are a little different, and the way they do things like manage installing packages might be a little bit different. Um, the Raspberry Pi OS, which is what we're running, is a customized version of Debian. Um, and it was customized by the Raspberry Pi Foundation for the Raspberry Pi hardware. That's why I started with that. Okay. Um, so, right. Okay. So, when you want to interact with, so how many of you guys have Mac uh, computers? Okay. And Windows for the rest of you then? Or anybody have a Chromebook? No? Guess what? Chrome OS is a Linux variant, and so is Android, by the way. So if you've been using a Chromebook, you've actually been using Linux. You just didn't know it. Um, okay, so the way you interact with the system graphically is going to be very familiar. Like, gee, what do you think that this little folder icon might be? Yeah, maybe where you kind of get to all your files, and it's got a structure and folders and hierarchy and all of that. Okay. So that part is going to be very familiar. You can drag and drop files, you can stick USB sticks into the thing to copy files, you can download stuff from Canvas and upload, all of those usual functions. That's all there. Okay. Um, but the way the file system is organized, for those of you who are on Windows, this is going to be a little different. For those of you guys who are on Mac, it's actually very similar. Um, your home directory is in a folder called home and then your username. And within that are the usual kind of folders you'd expect, your desktop, your downloads folder, all of that, right? You download something, guess where it's going to go? Right? You can move it if you want, but by default, it'll go there. Okay. Um, and you can make subfolders. So, for example, I made a subfolder for programming where I'll keep all the code and stuff as we work through things in class. But all of this is going to work very similar to what you're used to with any other modern computer. Okay. It'll tell you free space. So, for example, here, what is GIB? This is a kind of a fun pop quiz. Yeah, gigabyte. Okay, so what's the difference between a gigabyte and a gigabyte? It's the 1024 versus 1,000 thing. Okay, so how many bytes are in a kilobyte? Okay, what should it be? What should the answer to that question be? 1,000, because what does kilo mean? 1,000, just like what is a kilometer? It's 1,000 meters. Yeah? Okay, but back in the day, in the 60s, what did a kilobyte mean? It actually meant 1024 bytes, okay, because 1024 is a power of 2, and everything on a computer is a power of 2, right? And they're like, well, 1024 and 1,000, that's close enough. We'll just call it a kilobyte, okay? Now, this drives a lot of people, particularly the French, crazy, okay? So maybe 5 or 10 years ago, some people got together and said, okay, if you say kilo, you mean 1,000. If you want to say 1024, you say kibi. So they made up new prefixes for the power of 2 ones. However, saying the word kibibyte, you look and sound like a complete fool, right? Okay, now I'm old school because back in my day, when I walked uphill both ways in the snow to school without shoes, fighting off rabid pterodactyls, and I liked it, right? Um, you never had to worry about any of those things, Patrick? Yeah, okay. Um, yeah, a kilobyte just meant 1024, and a kilometer was 1,000. And it's like, I'm not an idiot, so I can keep these two things straight. Okay. But the abbreviation for Gibby, which is the 1024 base system, has the little I there. Okay. So anyway, I can see I've got a bunch of free space. You guys will have a little bit more because your SD cards. So the one that I've got in here is 32 gigabytes, which is more than sufficient. But yeah, okay. Um, So working with files, that's all going to be pretty useful. Familiar to you. Stick an SD card, a USB stick into it, download, upload from Canvas, whatever. Okay. What's not going to be familiar, because you probably never really had to do it, is popping open a terminal and doing stuff. Okay. Um, you guys on Windows, when's the last time you opened up a PowerShell? Okay, yeah. So basically, you'd learned it in computer classes, right? And for some of you, this is the class where you're first running into it. Oh, thank you for saying 242, by the way. Okay, so CS-242 is a class that we ran in the spring. For a variety of reasons, we're rerunning it this semester. Okay, so when you guys registered for fall classes back in April or whatever, CS-242 wasn't an option. It is now. Okay. So, and it will not be offered next semester. Okay. So, some of you, how many of you guys already took 242 last semester? Okay. So, you guys are in the clear, right? But if you want to, this might be a good semester to double up and take two CS classes. Um, and so, if you're interested in that, talk to your advisor and get it added and go through that whole shtick. Okay. It only has CS 111 as a prerequisite, same as this class, so you can all take it if you haven't already, if you want to. Okay. Yeah. McCartan Lim, and I think it's Monday, Wednesday, Friday at 15:10, 3:10. Is that right? Okay. Uh, though, yeah. Um, but we're not going to be offering it in the spring. We had to kind of rearrange a few things. So, particularly juniors that have not taken 242, I would strongly encourage you to go ahead and do it now because you want to get it done before comps, right? Um, so, okay, good. Yeah. All right. You got questions? Ask me or Dr. Westfall or Dr. McCartney or your advisor or whatever later. Okay. So, terminal. Okay. Um, we'll do a lot of things in the terminal. Most things that you can do in the terminal, you can also do in the file browser, but there are a few things that you won't. Okay. And we'll kind of just see these as we go. For example, when I did this if config, right, to get the hardware address for my Wi Fi, I probably could have gotten that same information graphically, but because I'm a little old school, right, I just know these commands and just do them. Heck, even on my Mac, that command would work. I do if config and I can see all of my network connections. Um, okay. Um, so, yeah, doing things through the terminal is a little different. Okay. Now, the file system here, everything, the file system starts with a forward slash. Okay. Uh, and then there are folders within that that are folders and files. Now, one of the things that's kind of weird about Linux is it treats everything as if it's a file, even devices. So when I was dealing with this SD card and I wanted to read the SD card and write it to an image, I was really reading what to me looked like I was copying one file to another, but it was really reading from a device and copying its data into a file. And Linux just managed all of that for me. Okay. Um, so, uh, and you see that the hierarchy here, the forward slashes are how you go down a layer of directories. On Windows, it's different. It's backslashes, and every drive has a letter attached to it. So most of the time, right, your C drive, so it's C colon backslash and then program files or whatever. Yeah. Okay. Totally different layout and stuff. Most of the programs are actually installed in, and this is kind of crazy, in a folder called bin, a folder called sbin, or in folders called user bin or user local bin. Um, but you guys won't have to install anything because I already pre-configured pretty much everything. Okay. Um, okay, so yeah. So let's get started with kind of what are we actually going to do in the class? Okay, what's the point of this class? All right, so to do that, let me just open up Python and let me just make some function. And actually, let me blow up the font size on this so that you guys can see it a little bit better. Okay, is that big enough to read? Yeah, okay. All right, so let me define a function. Um, okay, so if I do that, hello, hello of 2 prints it twice and so on. So I just made a stupid little loop and it's printing hello world. And let me actually blow this up slightly more. Okay, that's a little better. Okay, so nothing particularly fancy or complicated, right? Just a really stupid, simple Python program. And you guys all did stuff like this in 111, right? And then eventually it got more exotic. Um, but the whole point of a class like this is to sort of think more about, well, I typed in hello of 2 or whatever, and it printed some stuff. How the hell did that actually work? Right? Like how did it actually the processor executed and this stuff get onto the screen? Now, did you care about that in 111? No, it was magic as far as you're concerned. Okay. Um, and there was a man behind a curtain. Well, guess what? We're opening the curtain, okay, to talk about how this actually runs on actual hardware. Okay. So let's quit this and let me open VS Code. Okay. And let's write the same thing or something pretty similar to it in C. I'll just, oops, sorry, I've got to reconfigure some stuff on mine. Um, Come on. Okay, and the other thing, let me blow up the view a little bit. Appearance. Uh, let's zoom in. All right, so what was it? Control Shift Plus. Okay, so it's a little bigger so we can see. All right, so let me add a file, and I'll just do hello.c. Okay. Um, oh, looks like I forgot to do extensions for C. So, okay. So I'll let it do that real quick and we'll go back to here. Okay. All right. Now, I pre-configured this to have a terminal right there. Right now it's defaulting to the Linux terminal, but I think I can also throw in PowerShell. Doesn't really matter. It's just a terminal. Okay. So how do I see what's in a directory if I'm within a terminal? How do I see a directory within the graphical interface? Well, I just click it and bam, there's everything that's there. What about if I'm in a terminal? Okay, on Windows, how would you do this? You guys have never had to open up a terminal, have you? Oh, kids these days. So I'm going to type ls. Okay, ls in Linux will list the files that are in whatever directory I'm currently in, and I know what directory I'm currently in because that's the part in blue. So this tilde, by the way, is a shorthand way of saying /home/my username /. Okay, so tilde/programming is the same as /home/mechanic/programming, or in y'all's case, CSC student or whatever. Okay, which is a really nice shorthand than having to type all that stuff all the time. Okay, so so this is the blue part tells me, okay, I know which directory I'm in the terminal, and the terminal that's been sort of embedded here within VS Code is going to default to the folder that has the files that I've currently got open, my project. Okay, and you want to have one folder for each project that you're doing because that's just how VS Code organizes it. Okay, so I've got this thing that I've written. Oh, and I forgot one thing. It's not hugely important, but the compiler will yell at me, which is to return 0. We'll talk about what that means later. Okay, so does this look kind of like my Python program minus the loop? I didn't bother with the loop for this. So what's similar and what's not? Yeah. Okay, so I'm using puts here, or put s for put string, um, and instead of print. Okay, there is a print command. We'll talk about it later, but it's got some funny business with it. All right, what else? Yeah. Oh, that's only because I just didn't do a loop, right? Um, yeah. Okay, I defined the function differently. So when I defined the function in Python, I said def hello of in. Okay, did I ever specify what in was? Well, in C, I did. Okay, void, which is to say nothing. This program accepts no input, and it returns what kind of data? An integer. Hence why I typed int. Okay, so in Python, one of the things that makes it nice for teaching beginner programmers is, do you have to worry about what kind of variable or what kind of data you have, at least at first? Not really. You know, if you type 2 plus 5.3, it's just going to say, all right, 7.3, right? But that 2, how do you know that that wasn't an integer and the 5.3 was a floating point number? Okay. Now, not all of you guys took CS 101, period, and some of you did 106 or went straight to 111. Okay, but the way that those pieces of data are actually stored in a machine are not the same thing. Okay, and Python is nice because it keeps up with all of that for you and does a lot of stuff just to be nice to you. Right? You don't have to worry about a lot, and that's why a lot of it felt like magic. Well, magic's over. It's time for the dark arts. Okay, which is to say C in assembly programming. Okay, so I want to run this. Now in Python, how did I run it? I just did, right? There was nothing to do, okay? But that's not the case here. So if I want to run this, I first have to compile it using GCC, GNU C compiler, that's what it stands for. And I need to say, all right, I want hello.c is my source code, -o to hello. Okay, so this is the input source file, and there can be multiple of these if needed. -o tells it that the output I want is to a file called hello. And you notice, did I put an extension on this? It's not hello dot something. In Windows, what would an executable file have in this extension? .exe. In Linux, executables don't have an extension. I mean, you can put one there if you want, but they don't by default. Okay, so let me show you how you're going to know if you have an executable. If I type ls-l, it will give me a listing of my files, but it will do so in a slightly different organized fashion. I find this display to be more, it gives you more information. It's easy, and I find it easier to read, frankly. Okay, so how do I read all of this? So I just generated two files, hello.c and hello. Okay, how do I know that one's executable? They're green. Okay, now not every terminal will make them green, and you can configure what those colors are to suit your preferences. This is just whatever the default configuration is. Okay, directories are in blue, that's in green, and everything else is in the white type. Okay, so looking at the hello program, there's another way that I know that it's actually an executable file, and that's because of this X that's there. Okay, so every file has basically 9 attributes to it: 3 reads, 3 writes, and 3 executes. And it's who's allowed to read that file, who's allowed to write to that file, and who's allowed to execute that file. Okay, and you'll notice that there are the dashes. That means that, so for example, I, as the owner of this file, can read, write, and execute it. Then the others are basically, what about other users or the system user? Okay, so for the most part, you don't really need to worry about anything other than the first 3 there, because you're the owner of the file, and that's just kind of it. Okay, so I know, for example, that that's executable because of the X's, and because it also shows me in green, just to kind of make it visually obvious what I've got. Okay, and then, well, my hello.c, that's not an executable, right? So it doesn't need to have the execute attribute on it, because I'm not going to run a text file. It doesn't make sense. Okay, how do I actually execute hello? I'd like to run that. How would I do it? Well, what do you think? What would be logical? Of course, it's going to be ./ and then the name of the file that you want to execute. Huh? Yeah, I mean, that's all what you all were going to say, right? Yeah, of course. Okay, so that's how you execute something through the terminal. The ./ is critical. Okay, if I just typed hello, which is how you would do it in Windows, by the way, or DOS, it's going to say command not found. Okay, um, yeah, so there's good reason for that, but it may be mildly irritating, but you guys will get used to it after a week. Okay, all right, so when I ran this command here, a program, what I was doing was giving a program my source code, and it spit out an executable file. Okay, and then I was able to run that. Okay, so that process is called compiling. But really, there's 2 layers to it: compiling and assembling. Okay, and then really a third step called linking. When I typed that command, it did all 3 of those things in one swell foop, and I didn't have to think about the different layers of it. Okay, but we're going to peel back all 3 of those layers. Okay, and in particular, let's look at the actual file, the hello file. Okay, so let me start. I'm going to do a hex dump. Okay, so there is my source code file. Now, I don't know about you, but the thing at the bottom does not look like the thing at the top. even though they are the same file being displayed. So why do they look different? What the hell is going on there? Which one's more readable? This one or this one? Yeah, okay. So what I'm looking at here is actually how this is encoded as a file, okay? How is text stored in a computer? How's it encoded? You guys remember the acronym for it? It's an ASCII, usually, okay? Possibly Unicode, but for something simple like just C source code, it'll be an ASCII, okay? So the pound sign is the ASCII code, of course. It had to be that one, 69, okay? Which, by the way, is this the number 69 or is this something different? Okay, 69 in hex is what in decimal, right? It's 6 times 16 plus 9. Okay, we'll talk about hex later, so don't freak out right this instant. Okay, um, but basically, how do we count in the world? We count in base 10, right? And why? Well, look at your hands. Okay, imagine that you had 16 fingers, 8 on each hand. Just imagine a world where, and then imagine how children would learn to count if that were the case. And that's hexadecimal. Okay. All right. So each letter here or symbol is exactly two of these numbers. So 69 is the pound, 23 is the lowercase I. Actually, no, that's not right. Um, yeah, 69 is not the pound. All right, let's look up the table for it just real quick because 23 is like a um, oh. Yeah. Okay. Sorry. It's displayed. Oops. It's displayed in a funny way. I'll fix that. So the 2-3 actually comes first. So sorry. 2-3 is the hash mark. 6-9 is the I. 6E is the N. 6-3 is the C. And yes, that feels backwards. I'll fix that later. Don't worry about it right this instant. Okay. Um, but so every character is assigned exactly 1 byte of data to store it. And a 1 byte of data requires 2 hexadecimal digits to specify. Okay. The spaces. So, for example, you see some 2 zeros in here. Those are the spaces. Okay. And then the very last one, 0A. This is how I know that I've hit the end of my end of a line. Okay. And then there's no more data. Okay. So you see, for example, here I've got 0A, 0A. That's the 2 line breaks to go from line 2 to 3 and then 3 to 4. Okay. Does that kind of make sense? Yeah. All right. So great. But let me also do a hex dump of my output. Okay. So this is a much bigger file, right? And I can't just easily look at this in the same way as I did the text file, okay? Because this is actual code that's going to run on the processor, and all of those numbers mean something. Yeah. Just hex dump and then the file name. Well, the first one was hello.c, and then I just did hex dump hello to actually look at the executable. Right. So the hello.c was what we looked at first. This is the full blown executable. And you look at this and it's complete like it might as well be garbage from your perspective. Okay. Um, and okay, so but all of those numbers that are in there mean something. Okay, now there's a bunch of zeros in here, which is kind of padding some stuff off, and we can kind of ignore that. But the meat of it, if we kind of scroll up a little bit into, like here, right? Something's going on with all of that. Okay. And what all of that stuff is are the actual encodings of machine instructions to carry out the effect of this program, okay, which is to, in our case, write a string to the screen, okay, and then return the number 0 back to the spawning process, which in this case is the operating system. Returning 0, um, the 0 is, or the number that I'm going to return back is what's called an error code. And so if I return 0, that means the program completed cleanly, everything was good. And if I was trying to debug, I could put, like, let's say I thought my program was getting trapped over here before it quit, then I could put like return 1 there. But if it was getting trapped over here, I could put return 2 and then see what got returned. And then that would help me identify what the heck the program is doing. Okay. Um, okay. So, but how did I get from this to this? There were really 3 processes that happened there: assembling, or sorry, compiling, assembling, and linking. Okay. When I typed in the GCC command, it did all 3 of those things in succession for me. Okay. And took me directly from source code to executable. Didn't have to do anything in between. What we want to tease out, though, are the steps in between. Okay. So let me take this exact same program, this exact same source, and I'm going to do something else. Okay. What I did by adding this dash capital S flag was I told it I only want you to do the compiling, not the assembling and not the linking. Okay, so I just said just do the first third of the process. Okay, this has created a new file, which let me open it. Files. And let me change the syntax highlighting here to ARM64. Okay, so let's look at this. Well, we got a whole bunch of stuff going on here. And a bunch of instructions that I don't know what any of this means. All right. But let's kind of look through it that, okay, some of this, like this line, BL puts, does that look somewhat familiar? Yeah. My C program called a function called puts. Okay. Puts is part of the C standard library. Okay, so it's kind of like the print function in Python. Did you have to define how print worked? Right? It was there already for you. You could just use it. Okay. Same thing in C. Okay. And well, I also did some return. I returned. Okay, so maybe this ret has something to do with that. And then what did I return? I returned the number 0. Well, there's the number 0 right there. There's some LDP and move and add RP, and I don't know what any of that is doing. Okay. But I mean, I do. You guys don't yet. What you're looking at here is assembly code. Okay. So the hierarchy of code is you start with high level code like C or Python. All right. Or so we'll take C because that's what we started with. But high level code is abstracted away from the processor. Okay. if I wanted to execute this same program, like, so let's say I copied that executable over to my Mac, would it work? Why not? Uh, Partly. So yes, there's an operating system difference. But okay, let's say I took it to a PC that had Linux on it instead of my Raspberry Pi that has Linux on it. Yes. Python does, but not the C program, right? So if I took this executable that I just ran and copied it over to a Linux PC and tried to run it, would it run? And the answer is no, okay? Because what's different about the Raspberry Pi versus, say, the PCs that are sitting on all of the desks here? Hmm? Okay, yeah, it doesn't have, I mean, so let's say I had a monitor, keyboard, and all that, right? So I don't have to worry about the peripherals. But what's different about them? Huh? Okay, operating system, yeah. That's a software difference, though. What's different about the hardware? Okay, memory size, obviously physically it's much larger and more powerful. Who made the processor that's inside this Dell? Intel. Who made the processor that's inside the Raspberry Pi? Was it Intel? No. It was Broadcom with a license from ARM. Okay, so it's basically an ARM processor. That's a different processor architecture. So the ARM processor does not speak the same language that the x86 architecture in your most Windows computers does. Okay, now why did the Raspberry Pi? Why did they go with ARM processors? Several reasons. Well, all right. How many of you guys have an ARM processor in your possession right now? Everybody should be raising their hands. Why? Because guess what? Pretty much every cell phone or tablet or watch or earbuds or whatever runs, or the hardware wise, it's an ARM processor. Now, it might have been made by Qualcomm, like if you've got a Snapdragon, but the actual processor architecture was designed by ARM. Okay, ARM is a company. Okay. Um, and it's a different processor architecture to x86, which is what Intel designed. Okay, now x86 is very old. It was first designed for the 8086 back in the 70s. Okay, and then there was the 186 and the 286 and the 386 and the 486 and then the Pentium, which some people called 586s. And so could I take code that was written on a 1970s Intel machine and run it on my brand new 12th gen Core i whatever? Yes, which is mind blowing, right? But what it means is that the Intel architecture is this dinosaur of legacy cruft. It's just shit piled on top of more shit piled on top of more shit. Okay. The ARM V8 architecture is essentially clean sheet, starting over from complete scratch. Okay. So if I wanted to run this on my Intel machine, okay, let me make one other file and we'll compare. Um, no, I want. Okay, so I just generated a second version of this. Okay, now a lot of this looks pretty similar, but instead of BL, we have call. And there's this push and pop thing going on. There's a ret, okay? So this is the assembly in Intel language, okay, Intel assembly. The compiler is capable of generating either one, okay? And then an assembler would take, right, I'd use the Intel assembler for the Intel one and the ARM version for the ARM version. And then I would end up with executable code that I could run on one or the other machine. Okay. Now, it is possible to uh, run executables from one platform on another using an interpreter layer that basically fakes it and translates from one to the other, which we'll use from time to time just because it's handy. But essentially, with unless you had something like that, if I wanted to execute this Intel code that I just made, I would have to take it onto an Intel Linux machine to do it. Okay, so we're going to start with the class with mostly C programming, but the majority of what we're going to be doing is writing this. Oops, that's not the one I meant. This one. This stuff by hand from scratch. Okay, and thinking about how, like, fundamentally, how many operations did our program, the C program, do? It looked like it just did two things: printed a string and returned the number 0. That's it. Okay. And so how many lines of C code basically was that? Basically just two, right? I mean, yeah, I had some white space and curly braces and stuff, but basically it was just two lines of code. But those two lines of code became, 30 something in assembly. Okay. And the reason is that we had to break down um, you know, printing a string or calling this function in C was a single line, but in reality is several steps that have to be accomplished in a very particular order for this to work correctly. Okay, so is this kind of that's sort of the big picture point of a class like this. Okay, um, yeah. Now you guys are probably feeling a little overwhelmed at the moment, particularly with all this terminal console stuff. There is a steep learning curve at the beginning to get comfortable with all the Raspberry Pi, Linux, all of this stuff, right? So there's going to be the steep learning curve, plus we got C on top of that. The Linux stuff will start to become familiar after you guys practice with it. I've been looking around on YouTube to try and find a couple of like relatively short crash course type videos that don't suck, but also aren't like 17 hours long, uh, to kind of give you guys some resources for this. But there's this thing called Google. It's really helpful. You can find a lot of information on that. Okay, so um, everybody's got their Pi, and we now kind of have the idea what we need to do with our SD card and those two steps. Okay, so if you have trouble or issues with that, let me know. And I'll take a hand count of how many of you guys have the metal cases from Kit, because there's a part I'm going to need to order for you guys. Everybody else, you're fine. Okay? All right, good? All right, see you guys later.